Sorry about that. Okay. Now I start recording again. I'm sorry about that. Well, where were we? Oh yeah. So we have this example again where the nonlinearity is present in both equations. So computing the control U that makes this object linear, makes this guy linear, is not straightforward. That means we need to compute a coordinate transformation to bring this into that the so-called controller canonical form as mentioned before, which is where the input and the nonlinearities are all shoved or crunched into the last equation of the system, and then we can easily compute the control U. Okay. So the guy says here, define a new set of variables. Define a new set of variables. Z1, x1. Z2 is ax2 plus sine x1. Z1, then Z1 dot becomes minus 2Z1 plus Z2. Yeah, it's easy to see because this is Z2. This is Z2. Okay. And Z2 dot is 2 minus 2 Z1 cos Z1. Why? Again, you see, it's not an easy job. So Z2 is ax2 plus sine x1. Then you can extract x2 from this one. Is what? Is Z2 minus sine x1 over a. True? Is this correct? I have no idea. But actually I need to compute Z2 here. Z2 dot. So this is wrong. Nope. This is not it. Z dot. No. You just take d dt over this equation. So then Z2 dot is ax2 dot, okay, plus cos x1 dot. True? True? So now you just do the substitutions. Okay, and then you get this thing. Okay? 2z1 you have here. Why is it 2 here? I don't know. Because it's 2x1. Okay, fine. Okay. And you substitute z1 equal x1. Okay, so it's correct. It's correct. The final equation with z2 is correct. The equilibrium point is still 0, 0. And now you can easily compute u. Now you can easily compute the control u. U is 1 over a cosine 2z1 times v minus blah blah blah, all these nonlinear terms. So if you substitute this into this, probably you cancel all your nonlinear terms. The new dynamics is this one. This is the resulting new linearized feedbackly linearized dynamics. Okay. And then, of course, you compute v whatever. Okay. So it's not easy, you see. In this case, it was really easy to compute the coordinate transformation. However, in general, this is not easy. So what he says here, that's a very good remark. The result is not global. The result is not global. Okay. For instance, and he gives you some examples when the result is not valid, for instance. The input state linearization is achieved by a combination of a state transformation and input. Okay. Used in both. Okay. To implement the control law, the new states must be available. If they are not physically meaningful, they should be computed by measurable original state X. Okay, fine. Or you can do like you do, if you ask me, for the Kalman filter, you can do state estimation, or you can build an observer, essentially. That's why, for instance, in other lectures, they present you with observers. If there is uncertainty in the model, okay, there is an error in the computation of z and the, okay, well, we are not talking about these things in the sense that the models that we take into account in this lecture, they are kind of exact for tracking, control, whatever. Okay. What classes of nonlinear systems can achieve feedback linearization? This is a good question. And how do you find the proper transformation? So these two questions are the questions the guy is trying to answer, okay, later on. So you can do input-output linearization, okay, get a desired trajectory yd while keeping the whole state bounded, okay, fine. Now, how do you do that? Probably we have to take some to discuss something about the desired and the output. And the state code, I'm telling you the secret now. I'm sharing the secret. The coordinate transformation is going to be built by computing derivatives, some specific derivatives. They are called Lie derivatives. You have met them before when we were doing Lyapunov functions. If these are bound, then you can do the control canonical form essentially. The difficulty, the output y is only indirectly related to the input u. Okay, that means through the dynamical equations. Okay, fine. Input approach, generating a linear system input-output relation, formulating a controller based on a linear control. Okay, so these are the two goals to be achieved doing this whole procedure. And you have another example here. We have another example here, which is this one, which is kind of cute because but this is funny because you have the nonlinearities in the first equation, whereas the control is in the third equation. This is another awkward situation where you cannot straightforwardly compute u. It's not easy, it's not at hand. You cannot get it in one shot, so you need to do something else. So you need to generate, they say here, a direct relationship between the output y and the input u. Okay, and then you do this. You start differentiating y because the output depends on the states, but the states have dynamics. The states are characterized by dynamics. So the states have dynamics. Okay, then if the states have dynamics, then let's use them. Let's use them. How? Differentiate. Differentiate. You differentiate once, y dot. So you differentiate the output. Y dot is x1 dot. Okay. No, again, so what is the idea? Did you get it? Idea. Differentiate. Who? Who are you going to differentiate? Who are you going to differentiate? Hmm? Who are you going to differentiate? Hello? Okay, the mic is on.
The output.
Of course, differentiate y with respect to time, okay? Until when? Until what happens? Hmm? Until when? Until when? When do you stop differentiating the output? So you do y dot, y double dot,
Until we
y
reach
triple dot.
or
Huh?
until we reach a constant, or when the
Constant with what respect?
mm,
Not necessarily constant, but until y is almost something like a direct function of u. Until y is easily related to u. Of course, you cannot get rid of all the x's. But until y, y differentiated k times, has some sort of direct relationship with the input u.
some
Okay.
of the linear systems where the output is related with the input by the amplitude and phase. Uh,
Um, some sort of linear relation, indeed.
yeah,
Until you get some sort of linear. Look at this. Look at the example. You do y dot. Y dot is x1 dot is sine x2 plus x2 plus 1 x3. No relation to you. Okay? No relation to you. So you differentiate once again. Y double dot is what? Y double dot. Okay, so you differentiate again. And you get y double dot. Oh, sorry. And y double dot is sine, no, is cos x2, is cos x2 times x2 dot. Do you see the green letters? Or do I need to change
yes,
color?
they're visible on the black
Okay,
spectrum.
plus x2 dot plus 1 x3 plus x2 plus 1 x3 dot. Now the x3 dot, look at this equation, contains u, contains u, okay, contains u. So differentiating once again, okay, you do all the computations, you get this relation, some f of x, you don't care about f now, plus a simple relation containing u. F of x has this complicated form. We don't care at the moment. But if you get this relation, then you easily compute now the feedback linearization u. Okay. Of course, if you want to achieve other goals, you can compute v. For instance, v is given by this form, where e is the error. Okay, and you do tracking, whatever. I don't care about that. Okay, but if you pick v in this form, then the closed loop system satisfies this simple second order differentiable equation, this simple ODE of second order. Is it clear the goal that we need to achieve in general? Okay. Huh?
Yeah,
Okay.
it's okay. Okay.
The example, the controller is defined everywhere except at x2 equal minus 1. Okay, so to implement this law, he says here, this is a very good lecture. I'm glad I found it. Full state measurement is necessary because the computation of the derivative y need values of x. So you have to be careful. So maybe you need state observers, like we have other materials. If the output of a system should be differentiated r times, you don't know how many times. So, for instance, r times differentiable, okay? R times differentiable, okay? R times. Okay, to generate an explicit relation between y and u, the system is said to have relative degree r. Relative degree r. Okay, relative degree r. Okay. For the linear system, this relative degree is related to the poles and the zeros. For linear system is expressed in the number of poles. So what is the relative degree r for, how do you call this for linear systems? The number of poles minus number of zeros. How do you call this in the linear case? How do you say it in Romanian?
Sorry, how do we say?
How do you call number of poles minus number of zeros in Romanian?
Exces.
Excesul pol zerouri. This is, for the nonlinear systems, this is called relative degree. So recap from linear theory. Okay, if the transfer function single input, single output is B of S over A of S, okay, then degree, not grad because this is not Romanian, we are in English here, degree of A minus degree of B, okay, is called E, okay, it's called E, pole zero excess. Okay, this is wrong, but you know what I mean. Excesul pol zerouri. Okay, but this is called relative. In English, it's called relative degree. Okay, okay. So now we found something, a notion that is we are familiar with, a notion that we are familiar with. Okay, right. So for any controllable system of order n, he says here, by taking mostly n differentiations of the output, the control input will appear to any output. That means that in general, the relative degree of a controllable system is always smaller than the order of the system, less than or equal to the order of the system. If the control input never appears after more than n differentiations, the system is not controllable. So now we have another equivalent property for a system to be controllable. A system is not controllable if after n differentiations the system u doesn't show up. U doesn't show up in y. Okay, this is very interesting. This is related in the linear case. This is related in the linear case to pole zero cancellation. And I'd like you to check this out yourselves. Take a transfer function which is not irreducible. Take a transfer function which is not irreducible and check these properties. Check out these nonlinear properties. It's very interesting. It's very interesting. Okay. So what else do we do? Okay. Internal dynamics. A part of the dynamics which is unobservable in input-output linearization. For instance, the example, we have x3 x1 squared plus this. Okay. So the desired performance of the control based on the reduced order model depends on the stability of the internal dynamics. So the idea is that the internal dynamics, which is not seen, That's what we do in the input-output framework with transfer functions. Now you see again why dynamics is important in not only transfer functions. Okay, very nicely here. So now we can define, even for nonlinear systems, some sort of bounded input, bounded output stability. Okay, so if this unseen dynamics in the nonlinear systems is stable, probably the system is stable in the input-output sense. Example. We consider example 2. The control objective is the y to track a desired yd. If you differentiate, you immediately get an input-output relation. Then you get the control law, okay, which is defined, and then the error is defined by these dynamics. The internal dynamics, however, is this one. Is this one in the new coordinates. Okay. Now, since E and YD dot are bounded, okay, then X2 is also bounded. Then the system is stable because the whole trajectory is stable, not only the equilibrium point like we were discussing until now, but this is about the whole trajectory. So this is some input-output stability in the classic sense. We recover the classic notion of stability. Okay, we recover the classic notion of stability. Input-output linearization can also be applied to do stabilization, of course. And he explains here how you do that. Okay. Now, what happens? This is an interesting remark. What happens if the relative degree of the system is the same as its order? So that means what happens when you have a transfer function like this. Okay. Here the relative degree, okay, is 2 equal n. Okay. The relative degree, sorry, let's call it r this time because we are nonlinear people now. The relative degree r is 2 equals n. Excesul pol 0 e 2, exact ordinul sistemului. True? Okay. So the problem in this case is called input to state linearization. Okay. You don't have any internal dynamics whatsoever. In this case, you'll have the so-called zero dynamics of the system. This is also important because the zero dynamics is related to the observability. So this is a summary of what we have been discussing here. Okay. Let's have a break, and we talk again after the break. Okay. We do a little bit more and leave the rest for after vacation.